So hello everybody and welcome to today's WebCheminar. I'm Alex Russell, I'm from the Science of Synthesis team at Thieme Chemistry and I'm going to be hosting this Cheminar for us today. The subject of today's webinar is Rising Stars in Organic Synthesis, and I'm very happy that we've got 5 talks to you today from some young up-and-coming chemists showing quite a broad range of the chemistry that they're doing. First up, a couple of changes to the schedule. So first of all, Gary Molander was supposed to be chairing and introducing the speakers today. He won't be joining us today, so I will be taking over the introduction of the speakers. And secondly, Courtney Roberts, one of the speakers today, had something come up last minute and isn't able to join us live, but fortunately she was able to record her talk for us yesterday, and we will be playing a recording of this talk in place of her live talk today. Before we get going, just a couple of housekeeping notes about the Cheminar. So this Cheminar is being recorded. Once the session is finished, you will receive a link by email, and this link will be valid for you to watch the recording as many times as you like over the next 2 weeks. We'll be keeping the audience on mute during the web seminar, and unfortunately we don't have time for live question and answers during the seminar, so no verbal question and answers, but we would encourage you to use the Q&A window in the chat to ask any questions. These questions will be passed on to the speakers, who will then answer them in writing either later in the seminar or in the next or afterwards. And the Q&A will be available on the Chimie platform for the next 2 days. So check back after the seminar to see if your question has been answered. If you want to tweet about today's event, we're at Thieme Chemistry with the hashtag Cheminar. You might know that this is part of a series of Thieme Cheminars. If you want to be kept up to date and to register for future events, the link is here and will be posted in the chat, and also the QR code that you see in the bottom right-hand side of the screen also links to this page. Likewise, if you want to be kept up to date with what's going on at Thieme Chemistry, you can sign up to the newsletter, and the link for this will also be posted in the chat for you to read. Just a quick introduction to us at Thieme and what it is that we do. Traditionally, in terms of chemistry, Thieme has focused very much on organic chemistry, in particular organic synthesis, with our oldest journals, Synthesis and Synlet, being very well established and well known, covering primary research in chemical synthesis. This is complemented by SynFacts, which is highlights in chemical synthesis, where the editorial board choose their favourite papers published each month in their area of research. And more recent additions are the 2 open access journals, SynOpen, again covering synthetic chemistry, and organic materials, where the name says what it does. We have a database of pharmaceutical substances showing the industrially used synthetic routes to all important APIs, as well as the online reference work Science of Synthesis. A very new addition to the journals family is Sustainability and Circularity Now. This is a new open access journal just launched in the last couple of months, which is now available, open for submissions. This is a multidisciplinary journal, covering not just chemistry, but also materials and chemical engineering, with the focus being on green chemistry, sustainability, and a circular economy. So facing a lot of the, trying to find solutions to a lot of the serious problems that we're facing in the world today. So the Thieme Chemistry Journal Awards are awards made by the editorial boards of the Thieme Chemistry journals to young and upcoming chemists to recognise them at the beginning of their careers. So the board choose who they think are up-and-coming chemists and award these each year to an international group of people. In 2024, there were 107 awardees from 20 different countries, so really spanning the whole globe. Each year, Synlet then publishes a special edition with submissions by these awardees. In 2023, this was edited by Ben List, who was at the time the editor-in-chief of Synlet, and the 2024 edition is currently being edited by Deb Mighty, who has taken over from Ben as the editor-in-chief of Synlet. So a link will be posted to the most recent one of these special editions in the chat, so please take a look at this. Moving on to Science of Synthesis, which is an online reference work for organic chemistry. This is basically a huge series of critical reviews of synthetic chemistry and hot topics in organic chemistry. The authors of the reviews are some of the top people in each area, and they aim to provide a definitive overview of the most important methods for synthetic chemistry in the particular area that they're covering. There's a very broad range of chemistry covered in Science of Synthesis, and here at the bottom of the slide you'll just see a few of the most recent editions. So some sort of hot topics such as base metal catalysis and DNA encoded libraries, as well as maybe more traditional organic chemistry themes such as the synthesis of thioamides and diphosphenyl oral pincer ligands and asymmetric pi-al substitution reactions. So Science of Synthesis is overseen by a senior editorial board, which is made up of 9 organic chemists, so some of the most well-known names in organic chemistry. Since 2022, this has been supplemented by the Science of Synthesis Early Career Advisory Board. So these people were handpicked by the senior editorial board as being up-and-coming rising stars in organic synthesis. There are 30 people from all over the world are doing a mixture of, doing a range of different types of chemistry. And these are the people who we work with, who give us advice on what we should be looking at, where we should be going in terms of what we include in Science of Synthesis. And we're very happy today that of our 5 speakers, 4 of these are on this Early Career Advisory Board, and 2 of them have also recently been awarded the Thieme Chemistry Journal Awards. The Early Career Advisory Board for Science of Synthesis has a 3-year period. The current people have been on there from 2022 to 2024. We're currently looking for people to take over in 2025. So if you are a young chemist working in organic synthesis and would like to work with the editorial board and with Thieme to shape the future of Science of Synthesis, the nominations are open now. Likewise, if you know a young chemist who you think would be interested, please feel free to nominate. So that's it in terms of the introduction. Now we're moving on to the important part, so today's speakers. Our first speaker today is Professor Andy Thomas. Andy received both his BS and MS degrees in chemistry from the University of North Carolina at Charlotte. In 2011, he moved to the University of Illinois Urbana-Champaign to begin his Ph.D. with Professor Scott Denmark. Once he'd finished his Ph.D. in 2017, he began an NIH postdoctoral fellowship at MIT with Steve Buchwald, and in the fall of 2020, he joined the chemistry faculty at Texas A&M University. Andy's research group focuses on using physical organic chemistry to develop new synthetic methods by investigating the chemical reactivity of highly reactive intermediates. His research program has been recognized by several awards, including an NIH MIRA Award and an NSF Career Award. And today, Andy's going to talk to us about constructive ozonolysis capturing primary ozonides. So I'll hand over to you, Andy, for your talk now.
There we go. Hopefully everyone can hear me. Thank you, Alex, for that kind introduction. I'd really like to thank the team for organizing this and inviting me to give a talk today. I'm really excited to be here. So the title of my talk today is Constructive Ozonolysis and Capturing Primary Ozonides. And I'd like to do today is really give you an overview of where we are and our progress for these pursuits. But before we dive into chemistry today that I want to go into deeply about, what I'd like to do is give you an overview of my research program and what we've been working on since I started in 2020. There's 2 main areas in my group currently, and they both involve a couple outstanding synthetic challenges in organic synthesis. And the first area is carbon-lithium bond activation, which I won't be talking about today, but the overall synthetic goal here is to functionalize remote synthetic landscapes. So if you think about small molecule synthesis, for example, if you are a medicinal chemist, perhaps you may think that if you have some small biological properties from small molecules and you want to do structure-activity relationships, you can imagine how you might want to move certain groups and decorate the heterocycle at random locations. And to do that, typically you break the structure down into the common heterocycle that you can get, and then you use known chemistry to direct different groups around. And oftentimes, the embedded heteroatom is controlling most of the reactivity for these compounds. And so if you look at this nitrogen heterocycle, for example, the nitrogen really dominates most reactivity patterns. If you wanted to, for example, move the group out here, you could do a Friedel-Crafts alkylation reaction, direct amylation, perhaps, radical chemistry here. But to move at least 2 carbons units over is actually quite challenging in synthesis today. And that's really what my group has been focused on. For example, to bind a lithium and an organolithium, for example, to prevent it from binding the heterocycle and deprotonate new locations. But that's one area that we've been working on. What I'm going to talk to you more about today is our ozone activation to generate new ways to make carbon-oxygen bonds. Now, in my opinion, I think that the installation of oxygen into carbon frameworks is one of the most well-done organic transformations known to humankind, in the fact that you can make, epoxides very well, you can make alcohols really well, and carbonyl compounds. However, once you embed the oxygen atom into the carbon framework, it's really hard to functionalize it further. For example, you have to convert an epoxide to an alcohol typically, or a carbonyl to an alcohol. And then if you activate the alcohol, you typically react at carbon to do SN2 reactions or E2 elimination reactions. So it's quite challenging to make, for example, a dialkyl ether. And this is currently what we've been working on, is to generate bonds like this. And so what my group specializes in is to design new ways to react with reactive intermediates or study the chemical reactivity of subspecies. And the one that we chose was primary ozonides that had never been harnessed as a synthetic intermediate in organic chemistry into our first report in this area. Another thing that we do is we investigate mechanisms in various fields, such as polymer synthesis and things like that. We actually build rapid injection NMR apparatuses, and this is another area that we are focused on in CO2 activation. It's a big outfit with a couple collaborations with Luis Campos, Jim Hendricks, and Oswaldo Gutierrez, for example. And so moving forward today, what I'll do is I'll tell you a lot about our area in constructive ozonolysis, and we can talk about this another time with the lithium reagents if you're interested. But to go into this quite deeply, when you think about oxygen in organic synthesis or just bioactive compounds, for example, there's lots of different functional groups that are embedded into them that have ethers, for example, alcohols, and even peroxides in certain types of pharmaceuticals. And the blue boxes really are targeting bonds that we would like to be able to make either more efficiently or design new ways to do them, for example. Now, for the synthetic challenge that we're working on a specific area, for example. And so if we take a second and we look at this active pharmaceutical ingredient up here in the top left that was developed by Pfizer, the business end is really the aromatic or the flat groups over here on the left. And actually, they have very low solubility sometimes, pharmaceuticals. And one technique that is used is to install ethers or pegylated side chains to them that increase their water solubility. But the problem is they're really metabolically unstable. And so, for example, cytochrome P450 sees these CH bonds next to the oxygens, and it rapidly oxidizes them and decomposes your compound. And that leads to 2 scenarios. One, the lifetime in the body is very low. And the second one is you typically would need a lot of the compound to be administered. So, for example, you may have to go to the hospital to get an IV or something like that. However, if you could install stereogenic subunits next to the oxygen, you could tune those properties quite efficiently. And these types of bonds are actually really challenging to install that flank oxygen atoms, especially for dialkyl ethers, for example. And this is what we're currently working on here, is to make new ways to make groups like this. Now, you can make bonds like this on small scales, but it's quite challenging to do if you wanted to scale up or move a molecule to the clinic, for example. Now, to think about how you make carbon-oxygen bonds right now, you can start with an alkane, for example, or an alkene. And typically, these lead to very similar products directly. The alkanes can go to alcohols, carbonyls, esters, or acids, for example. Alkenes is another very prominent starting material to use to make an epoxide. diols, or even a monoalcohol, for example, or a carbonyl. As I was alluding to on the start page when we started the talk today, it's actually really hard to convert these into the dialkyl ether bonds, for example, to do that. But there have been folks that have worked on this, of course, in the past. And one such reaction that's currently still used is with some alkylation or ether synthesis. And that's typically done with alkoxide nucleophile with an organic halide. However, those typically lead to a lot of E2 reactions and things like that. So more often than not, a lot of times people use modified versions of those that use SN1 chemistry. For example, this acylation reaction here, where you take, for example, an alkyl halide with an alcohol with a Lewis acid, and you can make the ether that way. Another way to do this was developed by Jeffrey Bodie early in his career, to where he was taking these acetals and using the Lewis acid to generate an oxocarbenium that a nucleophile could then add into to make an alkyl ether, for example. And so some of you in the audience may be thinking, why don't you think about using cross-coupling reactions and things like that? And people have definitely done this. But there's a fundamental problem with cross-coupling reactions to forge carbon-oxygen bonds. Aryl ethers are quite effectively done with copper or palladium, for example. However, if you want an alkyl ether, for example, the reductive elimination barrier for carbon-oxygen bond formation is quite high. It's about 10 kcals higher in energy than most of the other pathways in general. And typically, the metals find other things to do, such as beta hydride eliminations and other things. And so this is where we came in to this area. And so I've always been fascinated with intermediates and reactive intermediates and things like that, and especially ozone in general. And so typically in organic synthesis, ozone is used to cleave CC bonds. And the way that this is agreed upon to work is you take ozone with an olefin. This does a 3+2 cyclo addition to give a primary ozonide, which can then rapidly revert to do a retro 3+2 cyclo addition to give this Kriege intermediate, which is this Zwitterion species here, plus an aldehyde. And under synthetic conditions, typically this Zwitterion is not as stable as you would want it to be. And so typically this cyclizes to give this secondary ozonide. And this is typically what's in the reaction flask when you do an ozonolysis reaction. And then after reductive workup, you get rid of the peroxide and you end up with two equivalents of an aldehyde or a ketone, depending on the olefin substitution patterns that you start with. Stuart Schreiber, when he was at Yale early in his career, what he was working on was to demonstrate how ozone could be used in synthesis. For example, you take an alkene, you ozonize it, and depending on the solvent or additives, for example, you can end up with different tailored products, such as an aldehyde ester, acetal ester, or an acetal and an aldehyde. And this really opened the door to get people to use ozonolysis reactions on scale, for example. And actually, ozone is used every day in industry and in academic labs and can be scaled up quite high. There's multiple avenues to make pharmaceuticals, ton scales, and also flow chemistry is a way to adapt these reactions to be more environmentally friendly or benign, for example. And in my opinion, I think that ozonolysis reactions are actually a very green way to do an oxidation, because you're just taking oxygen with electricity to make the ozone. And then typically you don't store peroxide on site. You can destroy it as it's generated in situ. And so to begin this project, Daniel Arriaga was my first graduate student. He took the reins here. And his Nature Chemistry paper recently came out, I guess, last year, middle of last year, where he was a co-author on this work. And what we did is there was a few things we had to do before we could really dive in here. And so one thing is, if no one's ever used a primary ozonide in synthesis, is there a reason for that? Are they stable enough to serve as a reactive intermediate, for example? And so when I started this area, I was calling primary ozonides transient intermediates. And I think that's really not the right nomenclature for a primary ozonide after we've been using it. And the fact that I think a transient intermediate means that you can't harness it in any aspects, and synthesis is currently the nomenclature that I'm using and what we'll use throughout the talk. And so to start with, what we wanted to do was we wanted to know how stable our primary ozonide was. And so what we wanted to do is we needed to make these and characterize them inside, to see what their lifetimes are and how stable they are and things. And so we turned to the NMR. And so what we did is we cooled the NMR down to minus 130 degrees with Freon gas. This is R12. This used to be in a lot of cars or refrigerants. It's CF2CL2 is the solvent with an alkene. And so the way these start is we actually have a bulb that we have a known volume of the gas, which we then condense inside of an NMR tube, which is over here on the right. And then we make solutions of ozone like this. And then we have a giant syringe system, which we lower in and inject the alkene of that into the tube inside of the NMR probe. And this is the proton NMR spectrum that we saw. And so I'd like to walk you through this. We have, for example, some CC cleavage here, which is a secondary ozonide over here on the left. This is Freon, our solvent. We have HA, which corresponds to this hydrogen here on the primary ozonide, and then the aliphatic chain. But this is at negative 130 degrees, and that's not very synthetically useful, for example. And so what we did is we rapidly warmed solutions of these up to minus 80 degrees. And what we found was a transalkene and a terminal alkene. The T1/2 is around 5 minutes at minus 80. And you can imagine that that's reasonably stable. And you can imagine how you could do this with flow chemistry or combined flow to do an addition reaction to something like this. Now, cis alkenes, they're not very stable at minus 80. The T1/2 or a cis alkene is about around 5 minutes at minus 100 degrees, so they're not quite as stable as the terminal and transalkenes. And so what we did is we started to add nucleophiles to the primary ozonide, and one of the first ones we did was isopropyl magnesium bromide. And what we found was that it could add in, and then after reductive workup, we ended up with the glycol here. And actually, glycols are actually quite easy to purify from these types of methods, because if you have any olefin left over or CC cleavage, they blow out of the column and the diol sticks to the silica, and it's really easy to manually handle this type of substrate scope in the laboratory. And so to start with, in our substrate scope, we did a lot of them in batch at minus 130 degrees to get an idea of the functional group compatibility for the substrate for the ozonolysis reaction, as well as the granular reagent. There's two reactive components here. And what we found was benzylated ethers, methoxy ethers, electron deficient groups, esters, chains, tartrate, for example, could be made. And also cis olefins can be done at this lower temperature for these types of reactions. And also terminal alkenes work quite well. We actually applied this to a couple pharmaceutical agents as well, such as the active ingredient in Mucinex, as well as this panisamide precursor here. But these 1,1 disubstituted olefins work quite well. Now, the issue here is that, we're really at minus 130 degrees, and you need a way to do this more where people would want to use this. And the way we're thinking was flow chemistry. And I also think that a project like this, you wouldn't have been able to attempt something like this about 30 to 40 years ago without the modern adaptation of flow. This would have been impossible, I think, especially with the flow being more prevalent now in synthesis labs. However, there is a conundrum here in how one does flow ozonolysis. And so typically what was done was heterogeneous flow conditions to where you blow a gas, ozone gas in, and then you mix that with the liquid in a syringe pump, for example, and you get what's called slug flow, where you have little bubbles in the liquid, and then the ozone diffuses in and out of the liquid, and the time it takes for that to happen is how long you run the reactions, or you can do annual flow. Now, another way that this has been done is you make an ozone atmosphere around the solution, and you have a permeable tube, and so you flow the solution with alkene and it flows in, and then the ozone diffuses inside, and then you can do your ozonolysis, a semi-permeable membrane. But for us, we really needed to do this homogeneous because you don't want a lot of ozone around or excess ozone, and you need to be able to capture it immediately once you make the primary ozonide. And one of the issues is that actually the solubility of ozone was not very well documented in the literature. The method you use to measure ozone solubility changes the concentrations, how you run the reactions, and things like that. And so we standardized this until what we wanted to do was to measure the ozone solubility first, and then we went back and did our flow reactions. And so the way that we did this is we took ozone, condensed it inside an NMR tube, and then we injected styrene into it, and we looked at the concentration of ozone in various solvents. Now, we measured a lot of organic solvents, such as methanol, dichloromethane, pentane, and ethyl acetate. And I don't want to walk you through this whole table, but there is actually a pretty neat thing that we saw, and the fact that, typically DCM is used. It's the most common organic solvent that's used for ozonolysis reactions, but the ones that we measured, it had one of the lowest solubilities amongst the solvents that's typically used for ozone. However, when we measured the rate of ozonolysis, it was one of the fastest. We couldn't actually measure the rate for ozonolysis in DCM. It was too fast, but it is quite significantly fast compared to the other solvents that we use. And so since we had tabulated this data, we could go back and then do our flow chemistry. But before we did that, we optimized the flow ozonolysis protocol. And what we do, this is a diagram of our flow system. And so we have the olefin dissolved in a solvent up here. We have nitrogen gas and ozone and concentration down here in DCM. We use nitrogen gas to push the ozone mixture to mix, and there's a mixer here, this T mixer, and this solution here. So you mix the olefin with the ozone solution here, and then you flow this out, and you can do a reductive workup, and we make ketones, for example. And this allowed us to really get a bird's eye view into this and allow us to develop this ozonolysis reaction quite effectively for standard alkenes. Now, one avenue that this could be used compared to other methods is it's really easy to control the equivalency of ozone so you don't get over-oxidation. And so with getting a handle on the solubility of ozone, the flow method set up, we went back to our primary ozonide synthesis, or what we have coined constructive ozonolysis. And so here, this is the new design of our flow apparatus. And so we've added an extra piston. And so the ozone solution is the same. There's a tube that goes to the bottom, and it makes it flow out. So we flow it out, it mixes with the olefin. And then there's another T mixer in the same bath where the Grignard flows in, it mixes, and it breaks it up, and then we can flow it out to get our diol products. And we did this with various alkenes. A trans olefin, we can make about 1.5 grams per hour, a terminal alkene. And also cis alkenes also work and flow at -80. Now, cyclooctene, that's a little bit cheating because the strain in it makes it a little bit more like a terminal alkene, actually, for strain purposes. It's a different type of strain, but they're less reactive compared to an open chain cis olefin. If you start to look here, you can see how the yield is lower, but you can see how we're starting to get some yield here with this cis alkene. Also, we prepared some pharmaceuticals in flow, for example, here, this terminal alkene active ingredient Mucinex, as well as the pranicamide precursor. And so this is quite easy to scale, and depending on the size of your reservoirs, you can imagine how you can flow this in. Another thing about this chemistry is, you're really generating the ozone solutions and using them immediately, and so you don't have to store large quantities of a peroxide on site. Now, this shows you the diol that we made when we first made the first paper here, but we've really not answered the question yet on the ether formation. And I think when we got back into this project, after we got the diol set up, our flow system set up, our rapid injection apparatus is set up, we rediscovered the synthetic challenge that we went after to solve, for example, that actually oxygen is actually pretty hard to functionalize after it's been pre-installed into the substrate. And so if we take a second and look at exactly what we're doing, now there's lots of mechanisms you can draw for how this addition reaction works. But with isopropyl magnesium bromide, we know we attack the middle oxygen first, and then the second equivalent of isopropyl magnesium bromide, does it react at the oxygen, the middle oxygen that was attacked, or can it react on the periphery? And I think the leaving group really matters here. And you can see here our yield was around 69%. And so what we're currently doing is doing multiple different types of Grignards. So you can imagine how you can add phenylmagnesium bromide or lithium diisopropyl amide, attack the central oxygen, and then change to a different nucleophile and make that a better leaving group here. We can actually see some product now for these ethers here, but it's too preliminary to show in today's talk. I don't know exactly how much time I have. I may be over time, I'm unsure. But today I'd like to conclude and say that constructive ozonolysis is proper, the word that we've coined here. And so ozone can be used in a constructive sense. And also this is a way to bypass osmium tetraoxide for reactions that you do not want asymmetric. We're currently trying to do this in an asymmetric fashion with flow, but we've not found an avenue to do that very effectively. yet. And also you should see very shortly, next few months, an organic synthesis procedure appear on the ozonation, constructive ozonolysis with the 1,1 substituted olefin. And I'd be happy to answer any questions from the audience the way that was described by Alex. But to end it off today, I have to thank my group. My group has been very stellar. None of this would be possible without them. The group has rapidly grown. I'd like to thank the funding agencies as well, and also our computational collaborators for some of the other work that we've been doing. And with that, I'll hand the floor back over to Alex.
Thanks very much, Andy, for some really interesting new possibilities in ozone chemistry, things that are quite new to us. Moving on now to our second speaker. Oh, sorry, before I say that, please do post any questions you have to Andy in the chat and he'll get back to you with any answers afterwards. So moving on to our second speaker, this is Professor Sidney Wilkerson-Hill. Sidney is currently an assistant professor in the chemistry department at the University of North Carolina, Chapel Hill. His research focuses on methods to obtain orphan cyclopropanes. Sidney Hill was born in Kinston, North Carolina, and began his undergraduate studies in North Carolina State University in 2006. He obtained a BS in Polymer and Color Chemistry through the College of Textiles and a BS in Chemistry through the College of Physical and Mathematical Sciences in 2010. In 2015, Sidney received his Ph.D. under the supervision of Professor Richmond Sarpong from the University of California, Berkeley, where his research focused on using transition metal catalyzed cycloisomerization reactions to access natural product scaffolds. He then became a UNCF Merck postdoctoral fellow with Professor Hugh Davis at Emory University in Atlanta, where his research focused on developing novel reactions using N-sulfonyl triazoles and rhodium tetracarboxylate catalysts for CH functionalization reactions. During his graduate studies, Sidney was also involved in diversity initiatives such as the Berkeley Science Network and the California Alliance programs to address the disparities facing minorities pursuing careers in the physical sciences. Since starting at UNC, Sidney has received the ACS Herman Fash Foundation grant, an NSF Career Award, the Alfred P. Sloan Award, the Eli Lilly ACC Grantee Award, the FMC Young Investigator Award, as well as the ACS Organic Lectureship, and of course the Thieme Chemistry Journal Award. So today, Sidney is going to talk to us about cyclopropane synthesis using palladium carbines. I'll hand over to you, Sidney.
All right, hopefully everyone can hear me and see my slides okay. Alex, thank you so much for the kind introduction. And I apologize to everyone for the last minute change in title. I wanted to be a little more general. We're not just talking about cyclopropane today. There'll be some four-membered rings too. So I'd like to, I'm really thrilled to be here today to share with you some of the work we've been working on over the last 5 years at UNC. Broadly speaking, my group is interested in all forms of divalent carbon, so carbines, carbenoids, and metallocarbines, and using those reactive intermediates to address problems in strain molecule synthesis. So when we started in 2018, excuse me, let me just get my pointer together. Okay. So when we started in 2018, we were really interested and focused on the synthesis of strained cyclopropanes. And we saw opportunity here because the physical properties of these strained molecules often translate into very important functions. And so what do I mean by that? So obviously cyclopropanes are the smallest carbocycle that you can obtain. By definition, they're planar because they only have 3 carbon atoms, but the 6 substituents around the ring are displayed in very specific regions of chemical space. These groups are sometimes referred to in medicinal chemistry as exit vectors. And so cyclopropanes are extraordinarily important in drug development for that reason, because they have well-defined exit vectors because of the planarity of this molecule. In fact, according to this review by Taylor and co-workers in 2016, cyclopropanes are actually the second most common saturated ring system found in drugs, only second to cyclohexanes. And when we consider both carbocyclic and heterocyclic rings, they're actually the 6th most common ring system found. So pretty important strain molecules. When we see these small strain rings come up and are in a variety of antiviral molecules, such as beclavir, lenacapavir, and nirmatrelvir. And I like really showing these three molecules because they really display the distinct type of flavors of cyclopropanes that you can encounter in drug development. So they really highlight some of the challenges for synthesizing these rings, which we'll go into in a second. Okay. So oftentimes, we're thinking about, when we think about complex molecules, we think about compounds that are large, that have large number of rings, stereogenic centers, and heteroatoms. But I wanted to argue that when you shrink molecules down in size, they also become very synthetically complex because limited disconnections are available, and these prevent rational structure activity relationship studies. So using cyclopropane as an example, we know that these molecules are typically obtained through a concerted 2+1 cycloaddition reaction because these are convergent and modular, but there are only 3 such disconnections of this type for this molecule. And so when we're thinking about building complex cyclopropanes like those found in drugs, not all of these disconnections will be viable. Nevertheless, there have been a variety of methods developed over the years to obtain cyclopropanes using things like sulfur ylides, zinc carbenoids, and metallocarbenes. And if I could actually just give a shout out to one of our speakers today, Vincent Lindsay. During my graduate studies, a lot of his work actually was inspirational and foundational for our work here at UNC. And these methods are excellent, and I'm not here to convince you that they're not used. In fact, when we think about molecules like beclavir, for example, people often have synthesized this cyclopropane using a Simmons-Smith methylation reaction because of this pendant Michael acceptor. But things become a little more challenging when we think about molecules like nirmatrelvir, which contain this dimethyl cyclopropane. You now have an all-carbon quaternary center within the ring. And so these methods using sulfur ylides, zinc carbenoids, and metallocarbenes started to break down when we're building these more congested alkyl cyclopropanes. And in fact, usually the way people address this challenge is by simply buying the dimethyl cyclopropane using chiral-pool reagents such as carine or chrysanthemic acid. And these are obviously excellent ways to build molecules, but the limitation here is synthetic efficiency because you're limited by the transformations you can do on this chiral-pool reagent, and then also the lack of modularity. If you did want to change the groups on the cyclopropane, there's no way to do that. So this really brings us to our challenge. When we started in 2018, our gap in knowledge was how do we transfer carbenes that are unactivated, unstabilized, and actually needed for these orphan cyclopropanes. And we define these types of strain molecules as those being derived from the transfer of an unstabilized or destabilized carbene intermediate. Another way to frame this challenge is how does one incorporate all carbon quaternary centers onto strain rings or nearby strain rings? And so over the past 5 years, my research program has developed 3 distinct themes. We're broadly interested in the functionalization of strain rings, using catalysis to access these orphan cyclopropanes, and then also reagent development, so moving beyond diazo compounds. And these silos are not set in stone. There's considerable overlap between the 3 of these. For example, a lot of the functionalization reactions involve catalysis, and we're very interested in developing new catalytic methodologies using the reagents that we develop in our laboratory as well. And so today I'd like to tell you 2 stories. One is on palladium catalysis, but I'd like to share a little bit of our work that we published last year in 2023 on strain ring functionalization, specifically using electron deficient boranes to accomplish this goal. And this all starts by thinking about that molecule nirmatrelvir, which I showed 2 slides ago, and how it's actually metabolized. One of the interesting things that came out of some of the studies from the researchers at Pfizer is that these dimethyl cyclopropanes are metabolized in very unique ways. And one of the ways is through oxidation at the methyl group. Now, this is not the only place on the molecule that gets oxidized by cytochrome P450s, but it's one of the ones that we're particularly interested in. And we can rationalize that because these Walsh orbitals in the strain member ring provide some activation to this CH bond. And so we were curious about developing new routes to compounds that contain groups that blocked oxidation at this cyclopropyl methyl position by the incorporation of fluorine atoms or all carbon, an all-carbon quaternary center. And this really brings us to what we call a retrosynthetic conundrum. And that is, how do you build teralkyl cyclopropanes? If you think about these proposed disconnections where we're using cyclopropyl carbinyl cations or cyclopropyl carbinyl radicals, we know these intermediates are well prone to rapid ring opening. And transferring carbenes to the corresponding teralkyl carbenes, these are prone to rearrangement. So these teralkyl cyclopropanes are what we call a unique class of orphan cyclopropanes by our definition. But we envisioned a potential solution. There's a really classic methods for synthesizing dialkyl cyclopropanes, which was published by Correa and Posner in 1967. Take the dihalocyclopropanes with organocuprates to do effectively a double substitution reaction at this position. And so we envisioned a similar process. What if we could actually take strain cyclopropenes that have some functionality and do an analogous type of substitution to now obtain more complex strain molecules that have the methyl groups fully functionalized. And to this end, we gravitated toward these electron-deficient boranes, such as tris-pentafluorophenylborane. The reactivity of this molecule is quite unique, and it's been thoroughly reviewed by Professor Rebecca Meelan and co-workers at Cardiff. But we saw potential advantages to using this molecule to activate strain rings. One of the reasons is it's extraordinarily oxophilic Lewis acid and forms many stable adducts, but it's also fluorophilic as well. So that gives us the opportunity for unique catalytic reactivity. And so we envisioned a process where we could potentially use this Lewis acid to ionize a functionalized cyclopropene and affect substitution reactions. But we saw other potential opportunities too to use this borane to do the activation of diazoesters, and this would represent a transition metal-free way to obtain cyclopropane. All right, and there are three pieces of literature that suggested that we could do this. Researchers at Dow Chemical had showed that you could take these perfluorocyclopropenes with antimony pentafluoride at 0 degrees and abstract a fluoride ion. This suggests that these types of CF bonds are weak in these substrates. It was also known that you could take tris-pentafluorophenylborane and activate what I would characterize as relatively inert CF bonds to arrive at spiropentanes. And then finally, the work of Padua and co-workers and numerous others, including Breslow, had showed that you can make CC bonds to these cyclopropenium ions with granular reagents. And so these were the beginnings of what we saw as a catalytic cycle. And so to this end, in 2023, we've published this study where my student Joey Mancinelli went in and wanted to test this idea. And so what he found is by taking one equivalent of this difluorocyclopropene, which is synthesized using the method of Olah and Kesh, and one equivalent of this borane in C6D6 at 23 degrees Celsius, we isolated in 45% yield this D5 triphenyl cyclopropenium fluoroborate salt. And that was a really exciting day for us in lab for a number of reasons. One being it showed proof of concept that we could activate CF bonds in this way, but it also demonstrated that nucleophiles readily engage with these highly electron deficient fluorocyclopropenium ions. And so what we believed was happening here is that the borane, being extraordinarily fluorophilic, abstracts a CF bond. This then does a Friedel-Crafts reaction with solvent. The borane, then being electron deficient, is able to abstract the second CF bond, which should be more reactive than the one in the starting material, to give you this cyclopropenium salt. And so we were able to, on the first pass, obtain X-ray quality crystals of this salt. We can kind of see really nice pi-pi stacking interactions here between the phenyl rings of the fluoroborate and the aromatic rings of your cyclopropenium ion, which is drawn in and out of the page. Okay, and so when we're thinking about how to turn this catalyst over, we immediately turn to fluorinated nucleophiles as a potential solution. We envisioned after the first substitution with the sialylated, we turned to sialylated nucleophiles as a potential solution. We envisioned after the first addition, the sialylated nucleophile would liberate TMS fluoride, which serves as a thermodynamic driving force to push the reaction forward, and also a way to turn over the borane catalyst. And this gave us a really interesting scenario because if we started with a cyclopropene that had two different groups, R large and R medium, we could potentially now obtain completely unsymmetrical cyclopropenium ions that contain three different groups. And if we're able to abstract the second CF bond, now your nucleophile has a choice to add to one of these three positions. And so as drawn, we would anticipate if your sialylated nucleophile is large, we would obtain vicinal addition products. Whereas if the sialylated nucleophile now is small, after generating this differentially substituted cyclopropenium ion, perhaps now the addition would happen ipso to this red sphere to give you now geminal substitution products. And this works in practice. We can take these difluorocyclopropenes with sialoketene acetals using 15 mol% of tris pentafluorophenylborane in 1,2-DCE at 23 degrees C. And just in 1 hour, we're able to obtain these double functionalization products. Using these bulky sialoketene acetals, we observe these vicinal addition products. The takeaway message from this optimization slide is a wide variety of electron deficient boranes work in this transformation. Ones that are not electron rich or electron deficient, such as triphenylborane, will also abstract a CF bond, albeit at higher temperatures. Other Lewis acids, such as titanium tetrachloride, aluminum trichloride, and triple barf, give really good high yields of the substitution products. TMS triflate, however, in this reaction does not only produces product in 6% yield. In some cases, we were able to do functionalizations in a way that led to further rearrangement. So when we reacted these molecules using cyclopropenes containing a pendant benzoate group, we found that the borane was able to ionize that group and affect a CC bond migration to give you these highly substituted cyclobutenes, where the benzoate adds back into this allylic carbocation. And finally, we were able to realize this goal of substrate-controlled reactivity and selectivity for these 1,2 versus 1,1 addition products. So as I showed you before, these bulky sialoketene acetals will add 1,2. Sialoketene amides, similar thing. If they're extraordinarily bulky, they'll add 1,2. So again, the nucleophile is trying to add in a way that avoids creating a carbon atom with two adjacent quaternary centers. When we use this siloxyfuran, however, we obtain this butynolide in 79% yield and 1-to-1 DR as a mixture of the C2 and meso isomers. We did try a variety of allosylanes. Unfortunately, they were not nucleophilic enough to undergo these addition reactions, and so these allostananes proved useful. 80% yield of this 1,1 addition product. And finally, these difluorosilylenol ethers actually provide products that result from 1,1 addition and 63% yield. Okay. And so that was pretty exciting to us. Okay, so for the sake of time, I unfortunately don't have time to go into the mechanism of this transformation, but I do want to say that we did show one example of CH functionalization in this regard. These transformations proceed to add the nucleophile once, all right? And we can rationalize that based on the endothermicity versus the endothermicity of this transformation when we're abstracting a CF bond versus a CH bond. Okay, and then we also showed using these electron deficient boranes that we were able to indeed activate diazo compounds. So switching gears now, with 10 mol% of this borane, we can transfer these carbene groups to styrenes, and I'm just showing a short scope here of the molecules that we were able to make. We published this work back in 2020, shortly after Professor Mealy and co-workers published a really nice study on similar reactivity in the journal Chem. Okay. So I want to switch gears a little bit and now talk about our work using palladium catalysis to obtain these orphan cyclopropanes. And to do this, we're using these alpha-alpha disubstituted hydrazone reagents. And a lot of this work really stems from thinking about how nature makes and uses strain molecules. So we're really interested in these chrysanthemyl skeletons because they are known to undergo rearrangements to other cyclopropanes, but also these branched hydrocarbons. These types of molecules are known as irregular isoprenoids and are characterized by non-canonical linkages between isoprene units. And so this caused a lot of controversy, in the early days, because folks were trying to understand how a terpene cyclase could stitch together isoprene molecules in non-canonical ways. And so it actually turns out these arise from the rearrangement of these cations. But we saw a lot of power in using these types of cyclopropyl carbonyl cations if we could actually control them. Perhaps if we could generate use a transition metal to stabilize these intermediates, we can now take these CPC metal intermediates and have them exist in equilibrium with their open chain tertiary alkyl metal form. Where in this case, we would expect beta hydride elimination to give 1,4-dienes, and in the other case, we could potentially trap these CPC metal intermediates to give now functionalized cyclopropanes. And so some of the questions we set out to answer in this regard are what factors impact stability of CPC metal intermediates, how do cyclopropane substituents and transition metal identity and oxidation state affect their reactivity, but also can we now trap these molecules to obtain natural product from cores containing these orphan cyclopropanes. All right, so to summarize 2 years worth of work, my student Nina Ritchie and Adam Zahara published in 2022 that we could take these aryl halides with these types of hydrozones. These hydrozones serve as our CPC equivalents. So using 2 equivalents of this reagent in palladium catalysis, we were able to effectively cross-couple an aryl group to these hydrozones to obtain these skip-dienes. And we also showed 6 examples of these vinyl cyclopropanes. And so at the time, this was really exciting to us because these types of aryl dialkyl vinyl cyclopropanes reminded us of the pyrethroid skeleton. And we saw an opportunity there to use this chemistry to build a library of pyrethroids. These molecules are important because they are ion channel blockers that are specific for insects and are often used to combat pests such as mosquitoes. And unfortunately, their biological activity has deleterious toxicological properties against beneficial pollinators such as honeybees. And so the World Health Organization has actually identified pyrethroid resistance in mosquitoes as a major impediment to combating malaria. And so we envisioned this platform as a way to potentially develop new pyrethroids where mosquitoes were not resistant to them. And this is no joke. This is a headline from an article in the New York Times. Our insect populations are collapsing for a variety of reasons: industrialization, climate change, but also our overuse of pyrethroid insecticide. So since then, we've synthesized over 30 of these dialkyl cyclopropanes using this cross-coupling methodology. You can see we're making some very structurally complex molecules using this transformation. And since then, we've actually collaborated with Corteva Agriscience to test these compounds for biological activity. Mechanistically, we envision that this reaction works by first palladium generating an aryl-2 palladium salt with the aryl halide. The aryl-2 palladium salt then reacts with a diazo compound that's formed in situ from the base-mediated decomposition of your hydrozone to give now a unique palladium carbene. This undergoes a 1,2 aryl migration to give a palladium pibenzyl, and that slips from A to 3 to A to 1 and undergoes a syn-carbopalladation event. This gives a CPC palladium intermediate that can do one of 2 things. It could either beta hydride eliminate to give vinyl cyclopropane, or it could beta carbon eliminate to give this tertiary alkyl metal intermediate, followed by beta hydride elimination to give skip-dienes. And this work this cycle is, and this transformation is based off of the work of Jen Boang and Barlawenga and Valdez and numerous others. Okay. The reason we need 2 equivalents of our hydrozone is because we observed substantial migration, substantial amounts of this butadiene, which arises from migration of this alkyl group into the carbene carbon presumably from the palladium-2 carbene. All right, since then, we've shown that we can extend this reaction to make spirocyclic cyclobutanes, which was a problem highlighted by Professor Eric Herrera in this Chem Review and published in 2014. So now instead of using these vinyl hydrozones, using allylated or crotylated hydrozones, we can cross-couple into the hydrozone and undergo 4-exotrig cyclization to arrive at the spirocyclic vinyl cyclobutanes. Again, we need 2 equivalents of hydrozone here because half of our material actually goes to this really interesting CH insertion product. So we obtain vinyl cyclopropanes as well. The student that led this project was Isaiah Erker-Frank, and he was really excited about really demonstrating the broad utility of this reaction for the late stage functionalization of drugs. So here I'm just showing the heterocycle scope for this transformation. We can tolerate indoles, quinolines, and pyridines, among other heterocycles. Isaiah went on to then cross-couple to a variety of more complex aryl halides, such as this intermediate towards canagliflozin, and this compound from the API Sigma Aldrich library. When we move from these crotylated hydrozones now to allyl hydrozones, we can obtain alkylidine cyclobutanes, and I'm showing an example here of generating spirocyclic alkylidine cyclobutanes from indomethacin methyl ester and also this diazepam derivative. All right, so the last slides I want to show you here are, how mechanistic insights are really giving us a unique perspective on these cross-coupling reactions. We're, a lot of the structural features of palladium carbenes are not well understood, and because these are fleeting intermediates. One of the things we notice is as we change the electronics of our aryl ring from electron-rich to electron-poor, we could actually control the product distribution of this reaction. So as we move to more electron-poor aryl halides, we observe more of this vinyl migration product and less of the products where this aryl group is incorporated. And so what this suggested to us is the migratory aptitude of this group plays a dramatic role in the reactivity of palladium carbenes. So my student Isaiah found that we could again take these allylated hydrozones, and if we cross-coupled these aryl halides to them, we could obtain alkylidine cyclobutanes. However, if we switch our cross-coupling partner to a group such as this bromoenone, which presumably has poor migratory aptitude, now we can suppress the incorporation of this group into the carbene carbon and exclusively observe the CH functionalization reactivity. And finally, if we switch now and just take out the cross-coupling partner and just use palladium 0, we can obtain these really nice 210 bicycles, also known as alsanes, and 77% yield. So my students are very excited about this reactivity and studying how the structural features of palladium carbenes impact product distribution. All right, so with that, I've kind of shared you 2 stories from our research program. I hope this shows you kind of the diversity of thought that's going on in our research group at UNC. And I'd like to thank my students for all their hard work. They're really the drivers of all the chemistry at UNC. I'd like to thank these agencies for funding and everyone for their attention. And Alex, thanks for the invitation. I'd be happy to take questions in the chat.
So thank you very much, Sid, for a really interesting talk showing a couple of new ways to really highly functionalized and highly substituted small rings. I'd just encourage anyone to submit any questions to the chat that they have. So our third speaker today, who unfortunately can't be with us live, but has pre-recorded her talk, is Professor Courtney C. Roberts. So Courtney is an assistant professor and the 3M Alumni Professor of Chemistry and McKnight Land Grant Professor at the University of Minnesota. Courtney obtained her BS in chemistry from Pepperdine University in Los Angeles, and then pursued graduate studies at the University of North Carolina at Chapel Hill, becoming the first graduate student in the laboratory of Professor Simon Meek. During grad school, Courtney developed rhodium olefin hydrofunctionalization catalyst using a new class of ligands called carbodycarbenes. After completing her Ph.D. in 2016, Courtney became a postdoctoral research fellow in the lab of Professor Melanie Sanford at the University of Michigan, where she explored CH functionalization reactions using high-valent nickel. Courtney began her independent career as an assistant professor at the University of Minnesota in the fall of 2019. And at Minnesota, the Roberts Group focuses on the development of D0 metal catalysts for alkyl-alkyl cross-coupling, as well as harnessing heterocyclic aryl intermediates for medicinally relevant building blocks. While at the University of Minnesota, Courtney has been the recipient of the Amgen Young Investigator Award, again, the Thieme Chemistry Journal Award, an NSF Career Award, the NIH Maximizing Investigators Research Award, as well as the 3M Alumni Professorship in Chemistry and the McKnight Land Grant Professorship. So Courtney's talk today is titled Access to Previously Inaccessible Arynes Using Transition Metals. So please, can we go ahead with...
All right. Thank you so much for the opportunity to present some of the research we've been doing over the last 5 years or so in my group here at the University of Minnesota. I'm incredibly grateful to the organizers of this for inviting me. I wish I could be with you live, but the very first graduate student to have joined my lab is currently defending at the moment. So this is pre-recorded, but I'm very grateful for the flexibility there. So I'm going to tell you today a story about a few of the students in my group, but I did want to acknowledge right away the really wonderful students that I get to work with. I can't feature them all, otherwise we'd be here all day, but I just want to acknowledge the incredible work that they all do, as well as I'm incredibly grateful to the funding that we've had in the lab. And the story I'm going to tell you specifically is funded by our NIH grant. So my research group started a little under 5 years ago at the University of Minnesota. We work in a number of different areas, including a little bit of photoredox catalysis chemistry. We really got started though with redox catalysis with early transition metals, and that's not something that you often hear those phrases or those words in the same phrase. But early transition metals are quite redox inert, and so we use redox active ligands to enable cross-coupling chemistry for CC bond formation. But the story I'm going to tell you today deals with how metals can actually enable us to learn a lot about arynes and to actually access arynes that were previously inaccessible. My group also works in developing aryne methodology, developing aryne reagents, as well as rendering aryne reactions regioselective. But unfortunately, I don't have time to talk about all of those today. So when we're thinking about synthetic targets, as this is a synthesis seminar, we're often thinking about the importance of heterocycles, right? We see a lot of heterocycles in pharmaceutical molecules as well as agrochemicals. What I want to specifically point out with these 4 molecules as sort of a nice class of molecules to study is the fact that we have a lot of 5-membered N heterocycles. And not only do we have 5-membered N heterocycles, we have a lot of them in a 1,2 disubstitution pattern to each other. And so we can see that the 1,2 disubstitution can be 2 carbon-carbon bonds that are ortho to each other. We can also see that they can be 2 carbon heteroatom bonds that are ortho to each other, or products of annulation. So when we're sort of thinking about the retrosynthesis for this type of molecule, what I'd really like to focus in on is a really great synthon, which is an aryne. If you're unfamiliar with aryne chemistry, it's a triple bond in an aromatic ring. And so that would look like something like this. And arynes are highly electrophilic, and so we could think of some nucleophilic synthon, maybe an organometallic reagent, reacting with our aryne, which is an electrophile. That would place a negative charge after the first functionalization at this termini, and then it could react with some electrophilic synthon. Think something like an alkyl halide. We can also see arynes reacting with a lot of heteroatoms as well. So we can think about making these bond disconnections and these bond formations through various heteroatom carbon bond forming reactions as well. And then finally, arynes engage in a lot of pericyclic reactions, including a lot of 4+2 cycle additions. And so these seem like really pretty ideal synthons to make these molecules in a single step in one pot. Right, and we can also think about how easy these would be to derivatize. We could think about just changing this aryl component out very easily and very quickly to assay any sort of activity we were thinking about assaying prior to the final drug molecule. So arynes are pretty fantastic synthons. If you haven't thought about how to make an aryne for a while, we'll just review that quickly. We can take some sort of a strong base, and that strong base can undergo or can initiate a deprotonation of a aromatic ring with a leaving group in the ortho position, and that ortho leaving group leaves, and then we form this triple bond. Then we can think about adding in a more specialized aryne precursor as well. These have been really beautifully developed over the years, originally synthesized by Kobayashi and coworkers, where we take a fluoride and activate that TMS group, and then that causes that triflate to leave. So again, it's an elimination reaction. So it's very common. There are other ways to make arynes, including in my own department, some really beautiful work by the Hoy lab with cyclizations to form arynes. But today we're going to focus on this elimination pathway. So in 2012, my very favorite paper came out. That was a computational and experimental collaboration from the GARG labs, partnered with the computational labs of Hauck and Payton. And so back in 2012, there's this paper called An Efficient Computational Method to Predict the Synthetic Utility of Heterocyclic Arines. And so this implies that we can't actually use all heterocyclic arines in synthesis, all right? And so what this paper did is it looked at the energy of the arine and the dehydrogenation energy. And this is commonly used in alkyne literature to understand if we can actually form these arines or not. So to illustrate what I'm talking about, they looked at and computed the dehydrogenation energy to form this 4,5 indoline, and it's deemed to be energetically accessible. Then the GARG group did this really beautiful validation of this computational result and used this 4,5 indoline motif in the synthesis and derivatization, actually, late stage of a natural product. Right, so this N-heterocyclic arine is incredibly useful. We see that it's unmasked at the end of the synthesis, so you can get multiple derivatives of this natural product. We can also see that 3,4-pyridine and the 6-membered N-heterocycle has been computed to be accessible. And we can see multiple syntheses actually use this synthon in the synthesis of ellipticine, which is a natural product. So people have been using arine intermediates for many, many decades to engage in bond-forming reactions in natural product synthesis. We can move that triple bond from the 4,5 position to the 5,6 position, and these are still accessible arines and have experimentally been validated. But what happens when we start to think about arines in smaller rings, I'll come back to this benzothiophene in a moment, is that the energy of these are computed to be so high for that elimination reaction to occur that they're energetically inaccessible. And experimentally, nobody has been able to actually do the elimination to form this 2,3 indoline. It really doesn't matter what your electronics are of this. If you think about adding a pyridine to this ring instead of a benzene, it doesn't change. We still can't access it. You can fundamentally change the structure of your heterocycle here to go from something like 7-azaindole to imidazopyridine, and still it's inaccessible, right? The ring strain from that bond that is close to a CSP hybridized having to be contained in that 5-membered ring is just too great, and so we can never form any of these arines. It also doesn't matter if we change the heteroatom from a nitrogen to an oxygen, as we see with this 2,3-benzofuran, we cannot access this molecule either. The difference between benzofuran and benzothiophene and why we can access benzothiophene, albeit with great difficulty, is the fact that the sulfur carbon bond is longer, and so it actually elongates that bond, and so it allows it to contain that triple bond within that 5-membered ring. And this is actually quite interesting because actually the first time anyone proposed in the literature an arine intermediate, it actually was benzofuran over 120 years ago. So people have actually been thinking about arine intermediates in 5-membered oxygen and nitrogen heterocycles for quite a long time. So looking back at those proposed retrosyntheses that I showed you, these none of these molecules can be made this way. This is not a viable route, despite the fact that it would have great utility if it was. So I'm going to switch gears for just a second here over to understanding how metals actually bind to pi systems and olefin complexes. So this is Ziza salt. This is a very famous organometallic complex. It's a textbook study of how metals bind to pi systems. So first off, we have what we would really think about as a filled CC pi bond orbital, sort of that normal metal to ligand interaction that we see, donating electron density into an empty metal d orbital. But what we also need to account for is the fact that the pi star orbital of the CC bond actually matches up phases quite well with a d orbital in your metal system. And if that metal has electrons in that d orbital, then we actually get donation from that metal d orbital back into the empty pi star CC bond. And this starts to break that bond when we add electron density into that pi star, and it elongates it. Not so much so that it breaks it, and this is what's described by the Duerchat-Duncanson model. a small amount of back donation, near sp2 hybridized in a bond order, close to 2, but not quite there. Metallocyclopropanes typically are invoked with early transition metals. We'll really be more focusing on this weak back donation. So what happens when we bind metals to arynes? Do we see this effect as well? Well, what we'll be looking at is the elongation of this triple bond. So I have what it's computed to be versus a benzene double bond. And we see as soon as we add a metal to that triple bond, we do see a slight elongation. And so this was sort of a clue to us that the Durechat-Duncanson model was in fact in play. And potentially we could think about leveraging to access an entire class of heterocyclic arynes that had previously been inaccessible. So really quickly, these nickel complexes were, the synthesis was developed by Bennett and coworkers from very commercially available or easy to make starting materials. You can use your favorite metal, nickel or palladium zero source, your favorite phosphine, whether it be an alkyl phosphine, an aryl phosphine, a monodentate, bidentate phosphine. There's a lot of different phosphines that work here. That nickel zero or metal will undergo oxidative addition into this nickel bromide bond. This is the first step of something like a Suzuki cross coupling. It's well understood, well established. Then we can take our base and that can activate our B-pen and do an intramolecular Suzuki reaction to generate a metal bound arine. So looking back at that class of molecules that computations and experiments said that we could never make due to the massive amount of ring strain that's built up into that 5-membered ring, we hypothesized that we could simply bind metals to it and alleviate just enough of that ring strain that we could actually access this class of molecules. This is a really fantastic team of students who worked on this. Jenna Humke spearheaded it. Erin Plaszek is the one defending her thesis right now. Really fantastic postdoc in the group, Roman Belli, as well as a younger graduate student, Sal Cargbo, and then Annabelle Ansel is a former postdoc that gathered preliminary data. So we thought to ourselves, metals could potentially alleviate enough ring strain here that we could access this entire class and many, many of the other 5-membered N heterocycles that I don't have listed on the page. So as I said, these are easy precursors to make. So we can use this commercially available aryl bromide here with the 7-aza-indole and the bromide in the 3 position. We can do an LDA borylation and deprotonate that and quench with borylane in a single step. We've now done this on up to 25-gram scale, and we can access a wide variety of other different N heterocycles. But I'm mostly going to be focusing on the 7-aza-indoline scaffold today. So we went ahead and followed that protocol, and we saw that oxidative addition into that metal carbon bonds with nickel cod proceeded quite easily in the presence of triphenylphosphine. Unfortunately, we could never get transmetallation to occur. And this is because after a number of different studies, we realized that the strain is quite large, and so it's energetically necessary for our nickel to rearrange the ligands so that these phosphines are cis to each other, so we can do that intramolecular transmetallation. And nothing was a driving force for that, and so we decided to lock those phosphines into a cis configuration so that we can do that transmetallation. So that involved doing a ligand exchange with dicyclohexylphosphine, and then we went ahead and were able to isolate this complex in over a gram scale. Now this is primed for a transmetallation of that B-pin onto our nickel. So we can get some crystal structures of this just to verify, nothing unusual about these oxidative addition complexes, but we see an aromatic CC bond length there between our carbon 1 and 2 here. We can go ahead and take a look at the phosphines. These are chemically inequivalent, and so what we see is 2 signals for them that each present as doublets as they're splitting each other. Now we added an activator to this, and our first clue whether we had actually made anything that we were looking to make is the phosphine NMR. So our J values actually contracted a lot, which is a readout of how much donation of phosphine is giving. So previously our J values for our phosphines here were 25, and now we see they're about 4. And this is because the phosphines and whatever we have made are far more donating than they were in the sigma aryl complex. And that would make sense if this was the arine complex, because we would need so much donation from those phosphines to back donate into that triple bonds. But we needed a crystal structure to verify what we had actually made, and we were absolutely delighted to see for the very first time we'd be able to access an inaccessible arine. So we're very excited about this idea and what it could do for the synthetic community now that we can unlock this new functional group for 5-membered N heterocycles. So we went ahead and took a look at some of the CC bond lengths. I'll bring in the cartoon chem draws here. We do in fact see the Duerchat-Duncanson model in play. We calculated the C1-C2 bond length here. We see it's 1.256 angstroms. Looking at the crystal structure, we see it's significantly elongated. But not so much so that it's double bond character. It still has the arine character, as we can see compared to that crystal structure of our sigma aryl complex. Turns out it's elongated even more than these already well-known and characterized accessible arine metal complexes. We can make a wide variety of substitution patterns, both electronically as well as sterically, and I'm just showing a sampling of these here. We can get the crystal structures of those as well. Now, why we really want to do this has to do with the utility of a new common functional group. So if we're going to make a desired library of heterocyclic molecules and we wanted to swap out our scaffolds, say from imidazopyridine to azaindole to pyrrolopyrazine to the spheropyridine, we would have to do that by building up each individual component, which could be quite challenging when you're thinking about how long it would take to synthesize each of these individual components. Alternatively, if we could have a common functional group that could suit any sort of N heterocycle that you would desire, we could have a common set of coupling partners and easily build up this library. So what does that say about the reactivity of these, right? So organometallic arine chemistry is actually quite well known, but these complexes gave us quite a surprise in how they actually reacted. So organometallic arines are known to be actually nucleophiles as compared to their electrophilic free arine counterparts that are not bound to metals. And so we see that here as well. So we're going to do a number of difunctionalization reactions, but we're going to first start to understand what the organometallic arine chemistry is. So we can react with an electrophile with excellent yields, such as methyl iodides. We can get a single regioisomer in this reaction. We can also react with other electrophiles like aldehydes as well as iodoniums, and these work quite well. So these complexes are in fact nucleophilic, as is well known for metal arine chemistry. But what we saw when we compared them to known metal arines is the fact that that C1-C2 bond length is elongated. So we thought that potentially this had differences in reactivity than what is well understood with 6-membered arines. And that's in fact true. These are ambiphilic complexes because they also react well with nucleophiles. And so this ambiphilicity really is quite advantageous when we're thinking about our coupling partners that we would like to react with these. So we can think about other nucleophilic coupling partners as well, both CsP3 hybridized carbons, CsP2 and CsP. Really interestingly, these have quite different regioselectivity depending on the hybridization of the carbon. Studying arine regioselectivity and governing it and controlling it and changing it is a big focus of my group. And so we're excited to look into that, but I don't have very many answers for you at the moment. So finally, we can think about not only nucleophilic and electrophilic reactivity of these arines, but the intermediate that they make is a well-known metal aryl complex. These are invoked as intermediates in things like cross-coupling reactions and Buchwald-Hartwig aminations, and so we can think about harnessing that for a second functionalization. So what that could look like is taking the electrophilic reactivity of our arine, reacting with it with a nucleophile, then doing a known functionalization to get this regioisomer of our 7-azaindole that is now disubstituted. But because of the really fantastic ambiphilic reactivity that we see here, we can actually react the methyl iodide first in this reaction, then the other coupling partner, and access the other regioisomer. And we can do this by simply changing the order of additions of our reagents due to the ambiphilic reactivity. So this is quite exciting for us when we're thinking of building up drug libraries. So I'll leave you with that. There's a lot of benefits of metal-bound arynes. We can do a lot of different types of chemistry with them as both electrophiles as well as nucleophiles. I'll point out we have a metal to play with, which makes you think about using oxidants such as CF3+ and F+ oxidants that can oxidize our nickel complex and then functionalize. And we can also do a number of annulation reactions as well. So with that, I'll summarize and say we prepare these precursors in a single step. We're able to exploit organometallic principles to access inaccessible arynes. We've developed a wide variety of aryne functionalizations. I'll go ahead and acknowledge my group again and thank them for the very hard work. And thank you all for listening and to the organizers for this really fantastic invitation. Thanks.
So even though she's not here to hear it, I'd like to thank Courtney very much for a really interesting talk. A lot of unusual arynes in there and some really interesting reactivity coming out of them. As you'd have seen, Courtney has given us an email address, so if you have any questions, you can also send them directly to her. Our fourth speaker today is Professor Emilio De Luca. Emilio obtained his bachelor's degree in chemistry from the University of Sao Paulo in 2008. After his master's in 2011 and Ph.D. in 2015, under the supervision of Professor Luis Carlos Diaz, working on the total synthesis of polyketides at the University of Campinas in Brazil, Emilio joined the research group of Professor Christina White at the University of Illinois Urbana-Champaign as a postdoctoral fellow. After a second postdoc under Professor Carlos Roque Correa, he began his independent career where, since 2018, he's been an assistant professor of chemistry at the University of Campinas. Emilio is interested in the late-stage modification of natural products for the synthesis of natural products with a higher degree of oxidation. In 2022, he was made a member of the Science of Synthesis Early Career Advisory Board, and in 2023, also to the JACS Gold Early Career Advisory Board. At this point, I'll hand over to Emilio for your talk on the use of CH bond oxidations in the synthesis of natural products.
Thank you, Alex, for your very kind introduction. Let me share my screen. I believe now can you see it?
Yes.
Yeah. Second. So it's a huge honor. Zoom quit unexpectedly. Alex, can you see me?
I can see.
Yeah, is everything okay?
Yes, everything's perfect. Yeah.
Okay, so it's a huge honor to be here today. So thank you for the invitation. So I would like to talk about CH bond oxidations in the synthesis of natural products, the work my group is developing here, University of Campinas, Brazil. And I would like to start with this statement. An atomistic change of a CH to a CO bond has the potential to alter physical and biological properties of molecules. For example, odor, while this Muget terpene with a CH bond here is odorless, the terpene with a CO bond here has a floral scent. Also in metabolism, while ibuprofen is not rapidly cleared from our body, 2-hydroxyibuprofen with a hydroxyl group here is rapidly cleared. And I could spend the whole day talking about these changes, but actually how traditionally we add carbon-oxygen bonds or oxygenated functional groups in molecules. We can think in textbook reactions like nucleophilic substitution, dihydroxylations, ozonolysis that Andy took to a whole new level and showed us today, olefin hydrations as well. But we can also do CH bond oxidations, and for now, we know a lot of methods from the last 20-25 years, like chemoenzymatics, allylic oxidations, photocatalysis, electrochemistry, organic oxidants such as DMDO, and metal catalysis, what I would like to talk a little bit more today. So what are the advantages of using a CH bond oxidation? We can talk about a late-stage rapid structural diversification, like in the work developed by Harrison in the diversification of fluoromethylene, a terpene. So, but what are the challenges associated with CH bond functionalizations? We can talk about the high bond dissociation energy. We can talk about low acidity, and also the profile and the energy of the molecular orbitals related with a CH bond. I would also like to include site selectivity. How could we design a system that would select, for example, this CH bond instead of any other in our molecule? And since many of the catalytic systems that we are using are electrophilic, how could we oxidize a CH bond in the presence of more electron-rich functional groups such as amines, olefins, or aryl rings? So how what we do now to avoid or to solve these issues, we can divide more or less CH bond functionalizations in the innate one, where, for example, we take a natural reactivity of a CH bond, like an allylic one, and we can do a specific oxidation mediated by selenium, for example. Or we can do guided CH bond functionalizations. For example, is a specific functional group will coordinate with a specific metal. We could have a metallocycle, and then after a functionalization, we can change a CH bond to a C functional group bond. For example, the work developed by Melanie Sanford back 20 years ago, where we could acetoxylate beta positions of oxines using palladium acetate and VAID. We can also design catalysts that could remotely oxidize CH bonds. For example, the iron PDP developed by Christina White in 2007. And I'd like to talk a little bit more about these catalytic systems that we are using in our systems here in Brazil. So if we go, since iron PDP is a electrophilic oxidant, we can oxidize more electron-rich CH bonds, such as the tertiary ones, using acetic acid as additive and hydrogen peroxide as the terminal oxidant. In 2013, a second version of this catalyst, the iron CF3 PDP, was developed, and we could also oxidize methylene to the corresponding ketones. Okay, since I already said, since the catalyst is electrophilic, the iron PDP will prefer to oxidize more electron-rich tertiary bonds, like in this system, where this CH bond is further from the electron withdrawing group than this one. So we got 5-to-1 selectivity. When it comes to steric effects, the CH bond in carbon 1 and the carbon 8 have a similar electronics, but since the acetyl group is pointed to this CH H bond, the oxidation will occur mainly in the C1 carbon. Okay. When we have electronic and sterics pointing to different directions, iron PDP will not be able to discriminate them, like the more electron-rich tertiary CH bond and the more steric exposed methylene bond, but iron CF3-PDP go mainly for secondary oxidation. So iron CF3-PDP prefers sterics over electronics. So we can see it in a more complex example like artemisinin, while iron PDP oxidizes mainly the tertiary C10 position. Iron CF3-PDP will oxidize mainly the methylene at C9. So in 2022, during the pandemics, my research group wrote this review article published on synthesis, and we realized that in that moment, only 4 methodologies were used in total synthesis of natural products. So the first one used was developed by the Schonecker and the Baron group, and it's a copper-mediated using imine as a directing group to oxidize primary and beta CH bonds. Okay, this is a direct one. Also, the Sanford methodology that I already said was used in total synthesis. And the chemistry developed in the White lab for allylic oxidations using palladium acetate bisulfoxide and parabenzoquinone as the terminal oxidant. In this case, if the nucleophile is a second molecule, we have an intermolecular functionalization, or if the nucleophile is already in the allylic molecule, we have an intermolecular system. Also, the iron PDP chemistry developed in the White group were used in total synthesis to oxidize tertiary, secondary, and also in the absence of acetic acid, we can get 5-member ring lactones. And what we realized in that moment when we wrote this review is all the methodologies, even the ones developed by the White lab, all of them were intramolecular processes. All of them used directing groups, and it showed us that maybe we are still very conservative when it comes to our retrosynthetic analysis. So we decided to try for the first time intermolecular oxidation in total synthesis of natural products. So with this scenario, Vitor and Eduardo, Vitor a PhD student and Eduardo, in that time an undergrad student, decided to use carenoic acid, a compound isolated from Micania glomerata, very prevalent in Brazil, decided to use carenoic acid as a platform to prepare more oxidized natural products. And also they would to validate known methodologies in a more complex scenario. So first, we started with carenoic acid and its corresponding methyl ester, and we performed allylic oxidation to deliver the enones in 38 and 55% yield using dipyridyl diselenide, and then with osmium tetroxide, we could get these 2 natural products in 44 and 75% yield. Okay, these were synthesized for the first time. We could compare our NMR with the isolated ones. After that, we moved to a more complex transformation. Okay, so we decided to validate manganese CF3-PDP, also developed in the White group. If we asked ourselves if we could remotely oxidize any CH bond in this carinoic acid derivative. And for our sadness, we got a complex mixture, which tells us that the catalytic system was not selective for this terpene. And since manganese CF3-PDP is also an electrophilic catalyst, we decided to add a carbonyl group in the D ring using isosteviol, a similar but different terpene from carinoic acid. And for our lucky, we could got 36% yield of the C2 ketone plus 5% yield of the equatorial alcohol in the C2 position. And I can tell you guys that I was happier with this 5% yield than with the 36 one. Now, if we think there is no simple way to oxidize this equatorial position or reduce this ketone in the A ring instead of reduce the ketone in the D ring. Since we got this compound, we decided to prepare two more known metabolites from Streptomyces griseus, and one of them with this alcohol in the C2 position. One thing I would like to add to this transformation actually is manganese CF3-PDP, like iron CF3-PDP, will prefer sterics over electronics, and the methylene in the C2 position is the only methylene neighboring two other methylenes. All the other methylenes are more crowded, so that's why we get oxidation in the C2 position. So we prepared the oxine in the D ring, and after the Sanford palladium acetox mediated deoxidation, we could got the acetate in 52% yield plus 26% of recovering starting material. A global deprotection, we could got our first metabolite in 86 and 37% yield. After the synthesis of this metabolite, we run a second protection in the acetyl group, in the hydroxyl group, to get the acetyl group in 95% yield. And then we move to the C2 oxidation and see if what we learned in a simpler natural product, we could get similar results for oxidation in C2 in this case. So with 10 equivalents of hydrogen peroxide at 0 Celsius degrees, using the RR enantiomer of manganese CF3-PDP, chloroacetic acid as the additive, and acetonitrile dichloromethane, we could got the C2 oxidation in 62% yield, favoring the ketone. When we reduce the temperature to minus 45 Celsius degrees, we could now get more the alcohol than the ketone in 53% yield, and lowering the equivalence of hydrogen peroxide and keeping the temperature at minus 45, we got exclusively the alcohol at C2 position. Okay, after the acetate deprotection and the methyl ester released, we got the second terpene in 57 and 56% yield. And this is actually the end of my first story that I would like to share with you. And the second one is also being developed by Vitor with a second diterpene, acanthoic acid, which we got from Amazon rainforest. We have a collaboration with people isolating natural products up there. And now this is the structure of acanthoic acid. And the first thing I thought was we could do a simple allylic oxidation in acanthoic acid, and we could got this natural product. When I gave acanthoic acid to my students, I thought in 1 week we could assure this synthesis. And what I can tell you is after more than a year, we still did not get this natural product synthesis done. What we observed after a lot of experimentation is using 3 equivalents of selenium dioxide in reflux of THF, we could actually got only 6% yield of this. It's still a natural product, but not the one that we were originally planning to synthesize. But we could got this pimarine in only 6% yield. We did a lot of experimentation in this transformation, and what we could get to was reducing the amount of selenium dioxide to 1 equivalent in now at room temp in THF. We could got 38% yield of this tri-in, probably after an allylic oxidation and an elimination, we can get these 2 double bonds here. Okay, an intramolecular deoxalder delivered this trachylobane, which is also a natural product, in 43% yield. We could access a class of natural products that originally we weren't looking for, so that was quite nice. Victor is now using acanthoic acid and the trachylobane backbone to access other oxidized natural products. And I believe this is the end of my second story today. So just a few conclusions. We could synthesize a few anti-carines and anti-begarines metabolites, 3 of them for the first time. And we could develop the first example of a non-directed metal-catalyzed CH bond oxidation in the synthesis of a natural product. So our hope is people could give a try to CH bond oxidation in the synthesis of natural products. Today we have a lot of selectivity rules, and they are reliable and predictable in many ways. So we found a few protocols that do not work in a more complex scenario, and we found room for invention. And we also found unexpected results, and pimarines can now be used as platform to assess other scaffolds. I would like to share just a few pictures of Institute of Chemistry and University of Campinas. Now, this is our main entrance. This is a view of a top view of our campus, and that's where the symbol of the university comes from. There is a night view of our campus, and now it's a moment I like to disclose a very important statement. It's George Lucas did not get inspiration from our campus to design Millennium Falcon. And finally, I would like to thank the Institute of Chemistry of University of Campinas to provide me a wonderful environment and facility to work. I would like to thank this incredible team I am fortunate to work with. FAPESP, CAPES, CNPq, and FIAPEX for the resourcing funding, and also Thieme and Science of Synthesis team for the opportunity to work with. It has been a great honor. Thank you.
So thanks very much, Emilio, for showing us some really interesting oxidations on some pretty challenging molecules. So moving on to our last speaker of today, Professor Vince Lindsay. So Vince received his BSc in chemistry in 2007 from the University of Montreal. He then pursued his doctoral studies with Professor André Charette, also at Montreal, and received his Ph.D. in chemistry in 2013, working on the development of asymmetric rhodium-catalyzed cycloproponations. He then worked as a postdoctoral fellow at the University of California, Berkeley, under the supervision of Professor Richmond Sarpong, working on the development of synthetic strategies to various nitrogen heterocycles, before beginning his independent career at North Carolina State University in 2016. Vince works on the development of novel synthetic methods involving strange ring systems. And today he's going to talk to us about sulfonyl cyclopropanols as modular cyclopropanone equivalents. So I'll hand the floor over to you, Vince.
All right. Thank you for the introduction. And thank you for the opportunity to tell you about our work that my group has been doing at NC State here in the last few years. And so our group work has been there since 2016 and work on strain ring chemistry. And specifically what I'll talk about today is the chemistry of cyclopropanones, which are these highly unstable and intermediate, which most of the time you can't really isolate them. And so what we do is we use these sulfonyl cyclopropanols as well-behaved equivalent of cyclopropanone for diverse types of transformations, such as the formation of other cyclopropane derivatives, ring expansion, as well as ring opening, ring closing transforms. But first I'll compare the chemistry of cyclopropanone to the closest parent, which is probably cyclobutanones, which unlike cyclopropanone is extremely common synthetic intermediates in organic synthesis, specifically in ring expansion type processes, which a good precursor for 5 or 6 membered ring formation using either more classical chemistry or more modern CC bond activation catalyzed by nickel or rhodium. And we've got an example here in a synthesis of fructose A, where cyclobutanone can be used for the formation of this spiral cycle by such a ring expansion through a semipinnacle rearrangement. And so at the onset of this program, what we really wondered is, even though cyclobutanone is extremely common, cyclopropanone is really rarely used as a building block in synthesis, and we wondered why that was the case. And if you dig deeper in the literature, you can actually see that there's a pretty large number of papers studying the fundamental reactivity of cyclopropanone starting in the 60s. And so even though that's the case, most of the time they use unsubstituted achiral cyclopropanone. The yields are pretty low in general, and it's really substrate specific. And so most of the time the scopes of these reactions are just a couple entries. And so to understand this better and why that's not really a general building block in organic synthesis, you can look at the strain energies of different carbocycles. And so kind of naively, you would think that since cyclobutanes and cyclopropanes have about the same strain energy, adding a ketone to these compounds should also react similarly. But it turns out that if you add a ketone to a cyclopropane ring, now that you have a very big difference in terms of strain energy between cyclobutanones and cyclopropanones. But that's not actually the problem and the reason why it's so unstable. If you know a little bit about strain ring chemistry, you know that 49 kcal per mole is not actually that high. And a lot of other building blocks have way higher strain energy and are perfectly bench stable. And so the main problem is actually their kinetic instability, meaning that they have a lot of fast, low energy decomposition pathways, and the main of which is the polymerization of cyclopropanone. And so it's actually known since the 60s that you can form cyclopropanone at low temperature using ketene and diazomethane. That gives you a solution of cyclopropanone, which you must distill and keep at -78, which is not the most practical thing. If you warm that up to room temperature, this is going to undergo a rapid polymerization, which is the main decomposition pathway that we have to fight in this chemistry. Other possible decomposition pathways are the light-mediated decarbonylation to form alkenes, or as seen in the Favorsky rearrangement, the addition of protic nucleophiles like alcohols would lead to a ring opening to acyclic esters like this. And so this is a schematic picture of the setup that you need to do to form this cyclopropanone solution. So it's not the most simple process. The distillation, in addition to this, has to be performed at -78. And as you can notice, you need to use diisomethane, which also requires a pretty complex setup to do so. And so potentially for this, cyclopropanone itself is not really used very much in synthesis directly. But what people have done since the 60s, if they really wanted to use cyclopropanone as a building block, is to use a cyclopropanone precursors, which most of the time are these cyclopropanol species that have a leaving group at the C1 position that can undergo elimination in situ. The most common of these is the ethanol adduct of cyclopropanone, has been popularized by Wasserman in the 80s and 90s. This compound can be a cyclopropanone precursor, but it is volatile and slightly unstable. But most importantly, it takes some pretty harsh conditions in order to trigger that equilibrium to cyclopropanone. And that's because the ethoxy group is not a great leaving group, in addition to the fact that we're forming something very high in energy and very unstable. And so because you need harsh conditions, that often leads to a lot of decomposition and low yields of the rearranged product. Also, the same compound has been known since the 70s by the work of Nakamura and Kuwajima to be able to equilibrate to metal homoenolate species, which is a very rich chemistry and very well developed at this point. So this works really well, but in our case, if you want to use that as a cyclopropanone precursor, that actually is a competing pathway that also contributes to lower the yield. So at the onset of our program, a key paper for us was this paper by Zili Chan that came out in 2008 that disclosed that sulfonic acid adducts of cyclopropanone could act as a very efficient equivalent of cyclopropanones. And so these not only are very stable crystalline solid, but most importantly, under very mild condition, can start equilibrating to cyclopropanone. And the only reported application at the time was this amine addition to cyclopropanone in presence of a terminal alkyne and a gold catalyst under really mild conditions to form these alpha alkynyl cyclopropylamines. And so we decided to study that a little bit further and first of all, develop a general method to make the chiral unsubstituted version of these compounds. And so starting from this commercially available silyloxyketal, you can cleave the TMS group using HCl. And then by addition of a sulfonic acid salt and formic acid, you can form these compounds directly without the need for purification. So they're pure only after an aqueous workup. And so you can do this on decagram scale really easily. And one of the reasons why we made so many of these derivatives is that we hypothesized that the nature of the R group on the sulfone could actually have a large influence on the equilibrium constant to cyclopropanone. And so we verified that by doing a little kinetic studies here using a pyrazole trapping reaction, where in this case, the slow step of the reaction is the formation of cyclopropanone, and the fast step is trapping with the pyrazole to form this stable adduct. And so because this is the slow step, then if you run this reaction with every one of these derivatives and follow this reaction by NMR, you can really see the difference in equilibration rates. And so what we observe is that obviously there's an electronic effect. So if you got a more electron poor sulfone here, that's going to lead to a better leaving group and a faster equilibration to cyclopropanone, like in the case of peronitro or para-CF3, for example. But there's also a steric effect. So if you have, for example, a terbutyl sulfone, that's going to lead to a faster equilibration to cyclopropanone compared to, let's say, a less hindered butyl sulfone or methyl sulfone, simply because in the case of a terbutyl sulfone, when you eliminate that group from the molecule, you have a torsional strain release, even though the ring strain increases in all cases. And so we can really have a wide range of equilibrium constant, depending on the nature of that sulfone. And that's really important because, as I said before, the main decomposition pathway that we're fighting in this chemistry is the polymerization of cyclopropanone, which means that we want to minimize the concentration of cyclopropanone at all times in these processes. And so every time we develop a new reaction with a different rate constant, we want to be able to go back and adjust that equilibrium constant to be able to basically have more optimization freedom and have a better chance to get high yields in these reactions. And so most of the time we try to use the most common of these compounds, these phenylsulfonyl cyclopropanol here, which is also commercially available at NME. But sometimes it's very practical to have other derivatives. For example, that para-CF3 has been very practical in some of our reactions. All right. So every one of these derivatives are all precursors of the same cyclopropanol, the unsubstituted achiral version. And by looking at the literature, we noticed that there was actually no general route to chiral substituted cyclopropanol. And so we decided to develop this with these sulfonyl cyclopropanol precursors. And so after looking at different possible route, the best way that we found to do this would be to take advantage of what's known in the literature to make sulfonyl cyclopropanes in high enantiomer selectivity. So there's a few methods already available to do this. And to simply develop an alpha hydroxylation reaction that would lead to the sulfonyl cyclopropanol. Now, the alpha hydroxylation of sulfones was unknown in the literature when we started this. So we really had to optimize this reaction from the ground up. And what we found is these specialized conditions using a bis-silyl peroxide and BF3 as a superstoichiometric additive. And so with these conditions, that leads to access to a wide range of chiral enantiomer-enriched cyclopropanol equivalents, having an aryl group at this position, as well as aliphatic groups are compatible. You can have a CF3 there, or a gem dimethyl, or a 2,3 disubstitution, as well as bicyclic derivatives as shown here, which are quite interesting when you think about it, as these are typical Favorsky type intermediates in organic synthesis, but that are stabilized under their sulfonyl cyclopropanol form. And so the mechanism of this reaction is quite unusual. At first, the reason why we screen Lewis acid like BF3 is we wanted to increase the reactivity of the Lewis acid, so simply activation of the Lewis acid. But it turns out that BF3 has a totally different role in this reaction. And the way that we know this is that all the other Lewis acid that were not boron-based would not work in the reaction. You absolutely need to have a boron-type Lewis acid. Also, that Lewis acid, or that BF3, needs to be added before the oxidant in order to get a reasonable yield, which doesn't really make sense if it's only acting as a Lewis acid. And so after some mechanistic study, what we found is that this is the mechanism. And so after deprotonation of the sulfonyl cyclopropane, you can obtain this organolithium region. This is going to react with BF3 to form a lithium trifluoroborate. This is going to then lose a fluoride to cleave one of the silyl group on the oxidant to lead to a monoprotected oxidant that's going to recombine with the BF2 compound to form this borate. That's going to undergo a 1,2 shift, similar to a hydroboration oxidation type mechanism to form the CO bond. And after quenching the reaction with acetic acid at -78, you can directly get the sulfonyl cyclopropanol. And one experimental evidence that we have for this mechanism is the fact that if you run this reaction without the oxidant, but replacing it with a bis-silyl pinacol region instead, you can get access to this pinacol borane and you can isolate this, showing that we indeed form a carbon-boron bond before we form the carbon-oxygen bond in the reaction. All right, so here's how the whole sequence looks like. It's only 2 steps from a methyl sulfone. And so to make our substrates, very often we use a pretty classical chemistry that was developed in 1992 by Tanaka and Suzuki, where you can switch an enantiomer-enriched epoxide to a sulfonyl cyclopropane through a series of SN2 reaction in one pot. And so you can take a methyl sulfone, deprotonate it. This anion is going to attack the terminal position of the epoxide. The new alkoxide that is formed gets activated as a leaving group. And then finally, an intramolecular SN2 reaction leads to the sulfonyl cyclopropane. And because these have pure SN2 character, you can keep the stereochemical information and have an enantiomer pure sulfonyl cyclopropane. After applying our oxidation condition, you can get access to sulfonyl cyclopropanol, and this is applicable to gram scale. Now, this epoxide is commercially available in its enantiomer pure form, but obviously it's not the case of every epoxide. So for other types of substitution, what we do instead of having to form the epoxide in an enantiomer pure form, we use hepichlorohydrin, which is a really cheap source of chirality. So this compound is less than $2 a gram in its enantiomer pure form. You can add a cuprate to the terminal position of that epoxide. This alcohol is going to cyclize under basic conditions to form a new epoxide, and then you can do the same sequence that I just showed you up there, shifting from an epoxide to a sulfonyl cyclopropane and then to a cyclopropanone equivalent. So if you want a different R group at this position, you just have to use a different Grignard in the first step, which obviously there's a ton of them that are commercially available. And we thought maybe we could switch the epoxide from a sulfonyl cyclopropane directly from hypochlorohydrin, and that could accelerate the process even more. And indeed, that works a little bit, so up to 35% yield. But something that we didn't expect in this reaction is that we would form also this bicyclobutane in 24% yield. And it turns out that these reagents are extremely practical in the literature. They're very popular these days for cycle additions and strain release type alkylation as well. But before this, it actually takes about 6 steps to make these reagents. And so we decided to optimize this reaction. This could be practical for the community. And eventually we got to decent yields, and we published this a couple years ago using a dibutyl magnesium or dialkyl magnesium as the base. And that was really the key for this reaction to be higher yield. And you can access these bicyclobutanes as well as houseanes in a single pot starting from hypochlorohydrin and the corresponding extended alkyl chloride. And so the way that this reaction works, well, first of all, since bicyclobutanes shown here are achiral, we start from racemic hypochlorohydrin, which is even cheaper, about 4 cents a gram. You can deprotonate the sulfone with a base. That sulfone is going to attack the terminal position of the epoxide to form an alkoxide here. And this is going to act as an internal base at this point to deprotonate the sulfone. Cyclization leads to a cyclobutanol intermediate, which is going to get activated as a leaving group. And then finally, a last equivalent of base deprotonates the last proton next to the sulfone, and a transannular substitution reaction leads to the bicyclobutane. So the scope of this reaction is pretty good. You can have substituents around the ring, electron poor or electron rich. You can have heterocycles there. You can also have aliphatic groups of different sterics, as well as a sulfonamide. And at the bottom of the slide, you can see the utility of these reagents that was developed not by us, but other people in the literature as strain release reagents. For example, the addition of nucleophiles or nucleophilic radical need to these cyclobutyl derivatives. If you have substituents on hypochlorohydrin, these are going to end up at different position on the bicyclobutane. So this works as well. If you have an extended chain between the epoxide and the alkyl chloride, through a similar mechanism, you can now access these houseanes reagents, which are also another type of strain release reagent, but this time to form cyclopentyl derivatives. And unlike the bicyclobutane, these are actually chiral. And so we wanted to show, can we access an enantiomer version of these houseanes? And indeed, because this is a series of SN2 reaction, you can actually do that. If you start from an enantiomer epoxide, you can transfer that stereochemical information to the houseane product. And so we have a couple examples of this. All right, so now back to cyclopropanone chemistry. And so now that we had access for the first time to chiral enantiomer-enriched cyclopropanones, we started studying their reactivity. First, starting by more classical chemistry, such as a Grignard addition to lead to tertiary cyclopropanols, olefination reaction that leads to alkylidene cyclopropanes. You can also do some CC activation using nickel catalysis to form cyclopentenones, or a one-atom ring expansion, either to beta-lactams or cyclobutanone derivatives. And so most of these are published, and I won't have time to talk about it. One last application that I want to discuss really rapidly that we published last year is the reaction between those bicyclobutanes that I just told you about and cyclopropanone. And so this is inspired by a method that was initially developed by Peter Whiff in 2021 on other ring-sized ketones, and we wonder if it was possible to do this reaction on cyclopropanone. And so it's actually known that if you take this sulfonyl bicyclobutanes and a strong base, you can deprotonate the bridgehead position selectively. That forms a nucleophile on this position. And under basic conditions, these sulfonyl cyclopropanol equilibrate to an electrophile. And so if you have these two compounds in a flask in presence of base, you're going to form a nucleophile and an electrophile. They're going to react together to form the corresponding bicyclobutyl cyclopropanol. And under Bronsted acid condition, you can protonate the middle bond of the bicyclobutane. That forms a carbocation at this position and triggers a semipinacol rearrangement that we call a strain relocating semipinacol rearrangement, forming these spiroheptanone compounds. And this is actually the only route to form chiral and then to enrich spirooctanones, which have importance as bioisosteres in medicinal chemistry. What I want to finish to talk with today is our new sub-program, I guess. If you add an amine to cyclopropanone, what we discovered is that the imiaminal that results from this is actually very, very stable, simply because the corresponding imine or iminium that would be formed by a condensation type process would be too strained. And so it prefers to stay as the imiaminal intermediate. And basically these imiaminals behave like cyclopropanols. And obviously the chemistry of cyclopropanol is pretty rich. You can do a lot of ring opening chemistry with cyclopropanol. But if you have an amine at this position, you're now at a different oxidation level, and that leads to new and useful disconnection. And so first starting for the formation of beta-fluoroamides, which we published last year, which are very difficult to access by other methods, as well as the formation of ring-fused indoles or pyrroloindolones, as shown here. And so, as I said, the chemistry of cyclopropanols is very rich and really well developed, where under basic conditions, you can form metal homoenolate species and then functionalize this beta position to lead to beta functionalized ketones. Under oxidative condition, you can form an oxygen-centered radical instead, and that leads to a beta radical, a carbonyl compound that's going to get functionalized in a similar way. And so this has been reviewed in the literature quite a bit. And so if you imagine adding an amine to cyclopropanone, this is going to lead to now a new oxidation level at this C1 position. And you can perform this ring opening either via homoenolate chemistry or oxidative condition. And what's really interesting in these types of ring opening is you can choose which bond of the cyclopropane is going to get cleaved, depending on the condition. So if you're under basic conditions, you're going to selectively cleave the less substituted bond to lead to a more stable beta carbanion. If you're in oxidative condition, it's going to cleave the most substituted bond of the cyclopropane to lead to a more stable, more substituted radical. And so you can be regiodivergent this way and access different types of products. At the bottom of the slide, I show a series of different hemiaminals that we found to be particularly stable in our conditions. And so first, the formation of beta-fluoroamides, which we published last year. What we found is that if you use a pyrazole adduct of cyclopropanone, which we used during our kinetic studies that I showed you earlier, and you ring open it under oxidative condition, this is going to lead to a beta-fluorinated acyl pyrazole intermediate. And so these are known to be reactive in acyl substitution reaction. If you simply use the crude of these compounds and add an amine, you can now diversify this position to lead to beta-fluoroamides. And so something that is probably not very well known is the fact that these compounds are really difficult to access by other methods. And so if you take an alpha beta unsaturated amide, for example, and try to add a fluoride to these compounds, this is usually a reaction that's in equilibrium and directed towards the starting material. And so it's not possible to form beta-fluoroamide this way. And so this is actually one of the only methods to access these compounds. And so you can have substitution on the cyclopropane ring, and you always have a complete regio control of the ring opening of the cyclopropane. And so you can have either the unsubstituted compound, a metal substituted, different types of substitution. If you use a bicyclic derivative, you can obtain these compounds with 6 or 5-membered ring here. You can have also a diversification on the amine with more complex amino acid derivatives. If you have a secondary amine, that can lead to tertiary amides. Even a Weinreb amide is accessible to this process. If you have an alcohol under specialized condition as nucleophile, you can access esters. And if you have a hydride, you can now access primary alcohols as well. If the initial nucleophile is an indole, you can form these hemiaminals, which are extremely stable. And so you can actually flash these compounds. They're really, really stable under a variety of conditions. But under oxidative conditions, specifically iron ACAC catalysis, you can actually oxidize them, and this is going to ring open to form a radical at this position. And since there's nothing like select fluor to functionalize this radical, the only thing it can do is cyclize at C2 of the indole. And after a final oxidation, that's going to lead to a pyrroloindolone. And so this works really well. The yield of this reaction are really good, and you can have substituents around the ring of the indole pretty much at any position. You can also have diversification on the cyclopropane ring, having substituents at these positions. And then you can also do it with a pyrrole, but although in lower yield, probably because of the cost of dearomatization is a little bit higher. All right, so that brings us to the end of my talk. I'd like to thank the people that did the work, my graduate students. You saw the names going at the bottom of the slides. So we have right now 7 graduate students and 5 undergrads doing really an amazing job in our group. I also like to thank NIH for funding this program, as well as Thieme for the invitation to talk here today. And I'll be happy to take any question as described by Alex in the chat and others. Thank you.
So thanks very much, Vince, for yet another talk on cyclopropane chemistry or cyclopropyl chemistry with a completely different spin on it. Some really interesting reactions in there. And yeah, as I said, the chat is still open, so please do ask any questions you have. This brings us to the end of our seminar today. I'd like to thank Vince and to all of the other speakers for some really interesting talks. I think that they've all lived up to the Rising Stars theme of today's webinar, and I'm sure we can all expect some great new chemistry from them in the very near future. If you do ask any questions, then remember to check back on the Chimie webpage for any answers that the speakers provide. And finally, I'd just like to do a quick promotion for our next WebCheminar. This is happening